So if ultimately what we are interested in is just the slope of a tangent line to the graph of a multivariable function at a certain point and in a certain direction in the xy plane, then what we're going to be looking for is a rate of change. We could parameterize the line like you did in the preview activity and then find the rate of change of the function per unit time, per unit of my parameter. But then in order to get an answer that depends only on the direction and not on the magnitude of my velocity, I ultimately need to divide out the magnitude of that vector that we used to determine the direction. So at the end of that process, what we sort of reason ourselves into is that the slope of the tangent line to the graph of f of x and y at the point P and moving in the direction of a vector v needs to be given by this same calculation that we just did here. So we can find the partial derivative with respect to t, but then we have to divide that partial derivative with respect to t by the magnitude of the velocity vector. And so if I write that in here, so the chain rule is what gave us the time rate of change when we have a parameterization for that line through the point in the direction that we want. But we want to do better, right? We want to... So then what we need to do to make it so that only the direction matters is we have to divide. And what are we dividing by? We're dividing by the magnitude of the velocity vector. And so that's going to be the square root of the sum of the squares. So dx dt squared, I'll write it as x prime of t squared plus y prime of t squared. So this is one way to kind of define what the slope of this tangent line is, but it's kind of a messy formula, right? I mean, it's not the end of the world, but it would be nice to have a simpler version of this if we can. And the way we can get to a simpler version is to notice that we have the derivative of x with respect to t in two different places here, right? It's a part of the numerator, but it's also a part of the thing underneath the square root in the denominator. Same thing with the y of t. And so it's probably a good idea if we can do this. So you mentioned a minute ago that this looks an awful lot like a dot product. Well, let's try to use that idea of a dot product as a way to sort of get closer to where we're trying to be here. So we could make this into a dot product. And the vectors that are being dotted here in the parentheses are a vector whose components are the partial derivatives of f with respect to x and y. So put in a comma there. And if I highlight this, can I do angle brackets? Yeah, okay, let me do angle brackets. So it's a vector whose components are the partial derivatives. And then we're going to take the dot product of that with, and now here's the vector that I'm going to actually make this into a fraction here. So the vector that we're taking a dot product with is x prime of t comma y prime of t. So I'll put that into my vector brackets. But then we're ultimately dividing by the magnitude of x prime of t, y prime of t. X prime of t, y prime of t. Update that there. So now here's where we're at. We can find this slope by taking the dot product of this vector, whose components are the partial derivatives of f, with a velocity vector, so whatever direction that we want. So this x prime of t, y prime of t is another name for our direction. And so the quicker way to write this, and this is probably the version of it that we're going to run with at the end of the day, is just to replace that x prime of t, y prime of t with the vector v. Because that was how we parameterized this curve, this line in the first place, right? Is we knew which direction that we wanted to go, and we made that direction the direction vector for our line. So I'm just going to replace this numerator with, replace the numerator with the vector v, and replace the thing we're taking the magnitude of down in the denominator also with the vector v. There we go. And so this makes it into kind of a nice looking formula, right? That what we do to find the slope of a tangent line in a direction which might not necessarily be the x or y direction is we take the direction, we divide it by its own magnitude. And in the process, what happens is whatever magnitude that vector originally had, that new magnitude gets shrunk down to 1. So when I divide a vector by its own magnitude, sometimes we call that normalizing the vector, because it takes the direction and it washes the direction away. Or sorry, it takes the magnitude and it washes the magnitude away, leaving only a direction. So unit vectors, vectors that have a magnitude of 1, are often how we think about describing directions without having to describe a magnitude. And I just compute this dot product, and that dot product is going to give me the slope of that tangent line, which we call the directional derivative in that direction. So so to compute a directional derivative, we take this vector whose components are the partial derivatives, and then we find a unit vector in the direction that we're interested in traveling, a vector of length 1. So if the vector doesn't have length 1 in the beginning, make it have length 1 by dividing it by its magnitude, and then find the dot product of that unit direction with the vector whose components are the partial derivatives. So your practice for 10.6.2 is to take this function, 3xy minus x squared y to the third, find its x and y partial derivatives, and then use this approach, so this is equation 10.6.3, to determine the directional derivatives in the I and j directions of these. And remember, I and j are the coordinate vectors 1, 0, and 0, 1. And then in part C, you'll use the direction 2, 3 instead and find a directional derivative facing in that direction. So in this problem, what you noticed with your teams was that if we compute a directional derivative in one of the coordinate directions, either the I direction or the j direction, what pops back out is just the partial derivatives in the x and y directions respectively. So this confirms for us that directional derivatives are just a generalization of partial derivatives, right? That in the case where our direction is the x direction or the y direction, then we just get back the x and y partial derivatives, which we expect because those are slopes of tangent lines taken in the x and y directions. But directional derivative gives us the flexibility to use other directions as well. And the only degree of difficulty is once we know which direction that we want to go in, we've got to find a unit vector in that direction, divide it by its own magnitude so that only the direction matters of the vector that we chose. And so in this example, when that direction was the 2, 3 direction, that magnitude ends up being the square root of 2 squared plus 3 squared, square root of 13. So not nice numbers, unlike our preview activity. But once we do that division problem, what we get is a unit vector that faces in the same direction that we're trying to walk, right? And then taking a dot product of that unit vector with the vector whose components are the partial derivatives of f will compute for us the directional derivative, which in this case is minus 2 over radical 13. So square roots tend to show up a lot in directional derivative calculations only because of the necessity of having that unit vector. And again, the necessity of that unit vector is so that only the direction that we choose matters and not the magnitude of the vector that we chose to represent the direction, which is something that we always want because we don't want that choice to matter, right? We want it to just describe a slope no matter what magnitude of vector we chose.